I send an email to him, see if he connects back.
Hello, hi guys, can you hear me?
Hi, Kaan. Good to see you here.
Great to see
I
you
think
too.
we'll be starting in about 3-4 minutes, and Muzdad will introduce you.
Okay.
You're coming soon online, I think.
Okay. Very nice to meet you, Govind, by the way.
Yeah, right. I'm Govind Agarwal, yes.
Yeah.
Hello. Hi,
Hi,
Kaan.
Mushtaq.
It's great to see you.
Great to see you too.
Hi, Govind.
Hi, Muzdad. Good to see you.
To see you too.
Let's see how many people we have. Yeah, 16 online, and there must be at least 30 people in the hall there. So it should be okay. There should be more coming in, I think.
We have a nice crowd here in Bergen 101.
Mushtaq, if you don't mind, do you mind if I just quickly try my screen share? I just want to
Yeah,
make sure.
please do it. I
Yeah,
think that's
please,
a good
yeah,
idea.
yeah.
Yep.
Can you guys see my screen?
Oh, yeah, I'm good.
Yep.
Okay,
Very
Looks
well.
great.
sounds good. Shall I stop screen share for now, or what's
Either way is
best?
fine.
Either way is fine. If you feel like this way, it's fine too.
Okay, let's keep it like this for now. Yeah.
Yep. Okay. So we'll hang on for a few minutes for people to arrive.
So Muzdad, we can wait maybe another 1 or 2 minutes, and then we can introduce Kaan.
Okay, sure. I'll wait for.
I see that 26 people have joined online, or there may be a few more come.
Okay,
We can wait
I'll
1 or
wait.
2 more minutes.
I'll wait for 2 more minutes.
2 more minutes, and then we can introduce.
Okay. And then perhaps we can ask someone in Gergen 101 to mute.
Yes.
Okay, great. Thank you. Yep.
I think we're approaching our numbers, like 36 people online. Maybe
Okay.
3-4 more will come. So whenever you want to start, you can start.
Okay. If it's okay for people in the room as well, it looks like they're all settled. Well, maybe we can get started. Hi, everyone. I'd like to welcome you all to today's colloquium by Kaan Akşit. We are very pleased to host him today. This is both a joint optics and data science colloquium, co-organized by the Institute of Optics and the Gurgen Institute for Data Science. But this seminar is also part of the Voices of XR speaker series organized by Studio X. For those who don't know, Studio X is the university's hub for extended reality. The speaker series is made possible by the Cathy McMurrin Murray and NSF through our PhD training program on augmented and virtual reality. In fact, students who are involved in the training program are supposed to attend this seminar as part of a required seminar in a course that they are taking this semester. So as you know, as you note here, so many different parties are involved in organizing this seminar. And I think this says at least two things. First, well, there's a lot of interest at the University of Rochester in augmented and virtual reality. But perhaps more importantly, this says that our speaker, Kaan Akşit's work is not only inspiring, but also lies at the intersection of multiple disciplines. In fact, Kaan's work is right at the intersection of light and computation, including computational approaches in imaging, graphics, fabrication, and displays. He is very well known for his contributions to display technologies dedicated to virtual reality, augmented reality, and three-dimensional displays with and without glasses. Kaan is currently an associate professor in computer science at University College London, where he leads the computational light laboratory. Previously, he was a research scientist at NVIDIA. He received his PhD from Koç University, his master's from the Technical University of Aachen, and his BS degree from Istanbul Technical University. He is a recipient of several awards in leading conferences on computer graphics and virtual reality. I met Kaan at a Center for Visual Science Symposium here in Rochester almost 5 years ago. And since then, I have been pleasantly following his contributions to the field. Without further ado, let me leave the screen to Kaan, who will tell us about whether holographic displays could be the key to achieving realism. Kaan?
Thank you, Müjdat, for having me here today. Thank you for your kind introduction. I would like to also thank Janik Roland and Govind for inviting me and hosting me at this seminar. So also thanks to everyone attending and for being here. So as Müjdat mentioned, I've been working on next generation display technology, and this talk will not be an exception. Precisely, I'll be focusing on holographic displays and their potential for achieving realism in display technologies in the future. So before we start, allow me to quickly introduce myself so that people seeing me for the very first time in their lives could get some idea about what I do, what I focus on. So I'm coming from a diverse set of experiences in industry and academia, and I joined University College London's Computer Science Department as an associate professor back in 2021. I started my research group, Computational Light Laboratory, and my research group's goal is to help shape young minds and get their attention to tackling a critical problem, the future of displays. Among the research committee, my contributions are primarily known for display technology, specifically augmented reality, near-eye, and autostereoscopic displays. Let me also briefly bring you a slide highlighting our most noticeable research work from recent years, and I'll walk you through each one of them one by one. So we showed that a simple film with pinholes could easily make a near-eye light field display from your smartphone, basically. And we showed that varifocal augmented reality near-eye displays could be a key component in the future's near-eye display for addressing focus-related issues. We showed also that most of the components in a near-eye display could just be 3D printed, including optics. We also showed new types of foveated displays with impressive form factors, and we also introduced various other means to improve resolution and eyesight in our displays. So beyond these works, we also support research outside of near-eye displays. Mainly autostereoscopic displays and stereoscopic displays were once a big theme in our research. Visible light communications was another, and gaze tracking using a single pixel detector with the help of deep learning is a relatively new research track in our focuses. Completely outside of our major focus, a recent collaboration with folks at MIT, we showed that speckle is actually a great way to detect material types. And you can just use deep learning to classify materials this way. It's helpful to create some smart personal fabrication devices that understand materials and helps the user and make sure that the user is safe while operating these devices. Now that I introduced myself, please allow me to describe the motivation of our research in general, and simply I would like to share why I'm so interested in my current research focus. Let me stop right at this moment and ask you this question. On a typical day, what do you stare at the most? Is it your loved ones, your partners, or perhaps your children? What captures most of your attention in life? So I would love to be there and just hear your comments on this, but I'll just give you the answer right away. I would say, like, ladies and gentlemen, it's your screens. You stare at the most at your screens. And those devices with vivid colors capture all your attention more than anything in your life. There are also studies for these kind of stuff. People spend a tremendous amount of their lifetimes in front of displays. It's more than half of the people's lifetimes in some cases. I personally find this a little bit weird, to be honest. I think this has to change or transform into something that is more human-oriented. However, I guarantee you that this amount will only increase in the future. We even wrote a vision paper on a potential future with displays back in 2021, as highlighted at the bottom of this slide. Given all these cases with our heavy usage of screens and so on, our scientific motivation is to invent and build the proof of concept future display systems for humans. So in the meantime, the industry and academia have been pushing forward with near-eye displays for virtual and augmented reality applications. So these devices are highly sophisticated engineering marvels due to the components involved in making them. Hopefully one day, we will be able to shrink our computers, optics, batteries into a pair of glasses form factor, so that we can use it on demand in anywhere, in any place. But there are just too many problems to tackle at once, as you can see in this list. If I dive into explaining these problems to you right now, I'm afraid we will run out of time, so I will avoid that. But even without talking much about the problems, you can easily see, and one can easily state, it's hard to build a device that includes graphics, computer vision, optical sciences, vision sciences expertise, user interface design expertise, mechanics, electronics, chemical components such as batteries, and just merging them into a single body is a large, heavy task. I should say that we need a way to avoid all these problems you see in this slide. A solution that would either solves or cleverly avoids all these problems remains to be seen. This is an outstanding issue, so it's an active research field. In my research, I argue that there might be an alternative way to get around this great engineering challenge, and that requires to change our perspective on the display design problem. In the rest of this talk, I will introduce you 3 primary research veins from last 2 years. Basically, I will show you how we are working to fix the issues related to augmented reality glasses and how we identify alternative methods for designing augmented reality glasses. Let me show you those 3 veins that I will introduce today. The first one is beaming displays. The second one is multi-plane computer-generated holography, and the last one is a foveated rendering method, ventral metaverse. Let me go ahead and introduce you to the beaming displays first, the very first one. So Here you see a depiction of all the known augmented reality display types. So I basically sat down one day and I looked into all these types, like retinal, near-eye, handheld, and spatial, and I built this figure. But in my observation, there is one display missing in the literature. There isn't a display or a display system projecting directly into a near-eye device or directly into the eye from some distance. To my knowledge, nobody has proposed such a display technology. Is it a sane idea? Let's try to understand. So as I introduce you this idea like projecting into the eye or projecting from some distance, people often just, think that the concept may be too hard to implement or not feasible at all. However, before we assess all this situation, I think we should look into something else first. Here you see a camera with a fancy lens, with a reasonable form factor, zooming into a building. You can even see the flag with the 13 stripes representing the original colonies. If you start to think about what a camera is doing here, what I'm proposing here is an inverse of this camera. It's a far less challenging case than a camera capturing all these details. So let me walk you through what we formulate. So we ask ourselves, what if we take everything off a near-eye display? Like computing modules, light modulators, batteries, basically all the active components. Instead, let's pack all these active components into the projectors and mount it on our walls. So the next bit would be to beam visuals from those projectors to the users from a large distance. And in this plan, a user only wears passive, lightweight glasses made of plastic lenses, mirrors, or diffractive components. So no batteries or no computational units on the face of the user or on the glasses. Such a solution will be just like your binoculars. It will be all passive, no battery power. So if we achieve this dream, let's say, we can avoid heating, form factor, weight, power, and computer-related issues fundamentally. We can change this paradigm fundamentally. Let me give you a slightly more detailed plan to realize the first version of the beaming display concept I'm talking about. Here you see a projector with some lenses to project an image from a spatial light modulator to some throw distance. And now you can see all passive eyepieces worn by a user. In this case, we combine a diffuser, 2 mirrors, and the lens. For sure, user will just be in different locations in front of the projector, so we need to find that location and we need to steer the beam accordingly towards the user so that the user can see some virtual image. And we eventually built this projector shown in the previous slide on an optical bench to see how much of it can be realized in real life. If you closely observe this photograph, you will see that an off-the-shelf projector is augmented with a series of achromatic lenses. Because we have different colors, we need achromatic lenses, right? And the output is steered towards a user with the help of a steering mirror on the left top, as you can see. Note that this build also has a coaxial camera, which helps track a user's location. So it's looking at the location where you beam your images, basically. It's trying to understand if it's, arriving at the right surface or not. So this is the projection side. Let's look into what a user should be wearing. So in other words, the eyepiece. Here we show the eyepiece a user wears on the right-hand side. So this eyepiece is a birdbath optics harvested from a previous generation of augmented reality glasses, and we combine it with a diffuser instead of a screen. The mirror at the top is optional, as one does not need it if the projection is from like ceiling or so. So the image that you will be seeing as you wear this is also shown here as in this photograph. We captured it using a camera at the location of the eye. We can provide up to 7 cycles per degree with a 35-degree field of view, which is very limited if you think about, the existing augmented reality displays or where we need to be going. It's very limited with respect to that, but that's okay. That's a great start for, exploring this concept. you can also ask like what happens as a user moves and what happens, like with the tracking and so on. You see a view from the eyepiece. This time we mount the eyepiece on a robot arm, as shown on the bottom right. And this demonstration could give you an idea about tracking performance of our system as the user moves or tilts his head to different locations or rotates his head and so on. You see that the tracking does some good job, let's say, in finding the locations. But you should also keep in mind this is not perfect, so this is just the start of a new concept. So we ask ourselves, how can we make it more perfect? How can we make it as in the way we are planning? So given the resolution and the field of view limit in beaming displays, given they are very limited, 7 cycles per degree and 35 degrees field of view, we started to garner interest in exploring an emerging topic, computer-generated holography, to build a holographic version of the beaming display. But along the way, we need to invent several different recipes to generate images with holography, and we need to make it realistic looking. So today, I will only focus on one of these recipes. There are many other recipes we built. This recipe is about a method to generate realistic looking 3-dimensional holographic images. So before we dive into this recipe, I think we should first understand what a hologram or a holographic display is. So there are important reasons behind people getting more interested in holographic displays nowadays, and this is because they can take advantage of extra dimensions found in the light's characteristics. And these include polarization, amplitude, phase, interference, and diffraction. And these displays can offer many different things with respect to conventional ones. And the first thing that they can offer is the resolution improvement. They can provide better resolutions than the conventional methods with the help of utilizing all this polarization, amplitude, and phase and diffraction characteristics. These displays can also offer accurate dark levels and extended high dynamic range. This is another promise of holographic displays. So another promise is related to the light sources it uses. As these displays use laser light sources, in principle, you can get a wider color gamut. You can also achieve that. We know that holographic displays could promise, let's say, 2D and 3D images at any desired depth. And we know that holographic displays do not have the concept of a dead pixel, because a scene is a result of a combination of pixels on a hologram. If one of these pixels fail, it's okay, because the other pixels could compensate and could help build, the scene entirely. Promises of all these promises of holographic displays are not limited to this. There are obviously many other things that we can discuss, but I'll keep it short. So all these promises listed here are not yet fully realized in a single holographic display, making computer-generated holography a critical research problem and an active research problem in the field. So let me also give you a description about what a hologram is. Again, I will simplify things to make it easy to understand and so on. So let's look into the definition of this hologram. The hologram is the usage of when people say hologram, they refer to the usage of diffractive optics or usage of interference and so on. These diffractive optics come in many shapes and sizes, of course, and the one I'm particularly interested in is also known as diffraction grating. And this diffraction grating, for sake of simplicity, let's assume it's just manipulating the phase of light, but not the amplitude. I choose this one because it's slightly easier to describe, and it's also common for various different reasons, but I'll not dive into that. So let me show you what I mean by this diffraction grating. An oversimplified version of this diffraction grating is just a bunch of different blocks with different heights, and each block can be is about 1 to 10 micrometers in size. let's assume that the surface of each block is a mirror for sake of simplicity, and let's assume that the height differences between blocks are in nanometer scale. So when you illuminate such a surface with a light source, light will eventually bounce, right? And if that light source is spatially coherent and also temporally coherent, multiple of these reflections with the help of reflection and diffraction will eventually generate some image at some desired plane, as the light rays will arrive on that image plane and interfere with each other. So you must have seen such patterns in the past. If you point a laser pointer on a wall, you get these speckle, these noisy patterns basically. And if you control the height of this diffraction rating for each block, basically how much delay you just want to generate for each pixel, if you control that, you can generate images like this one shown on the right hand side. So this is a crash course on what is a diffraction and what is a holographic display. So let's try to materialize this a little bit better. So a partially or entirely collimated light source, such as lasers, illuminates something called a spatial light modulator. It's a programmable diffraction grating or programmable phase-only hologram. People also call it like that. And with the help of that thing, of course, you can buy these things from multiple different manufacturers. I will list some of these things on the left-hand side, as you can see. And if you connect this to some computing resources, you'll be able to calculate your holograms for basically optimize your diffraction gratings and generate images at some desired depth. So as the light diffracts from the spatial light modulator and interferes at some desired distance to generate the targeted light field, you can see that an image is going to be formed at some distance in front of this spatial light modulator. So optimizing that diffraction grating is the problem, computational problem that one has to deal with. So for generating three-dimensional images, this could be a little bit of a complex task, let's say. Let me describe you why this is a complex task. In real life, when things are in focus, they look sharp. And when things are out of focus, they look a little bit blurry, right? This blurriness is depicted in DEF. As you can see, things look blurry and the transition of this intensity is smooth here. But in a holographic displays, since we use coherent light sources, it's often the case you see these ringing artifacts appearing when things are defocused. And in conventional algorithms, this causes some interesting artifacts appearing around the edges of objects in the scene. We propose a method to generate three-dimensional images without having these effects in place, so without suffering from all these ringing artifacts, basically. Now I'll go ahead and describe what we have built in computational terms. So allow me to walk you through this 3D hologram generation pipeline, let's say. So the green boxes on the left-hand side show an RGB input with some depth information, and our pipeline runs for each color primary separately. As depicted on the purple box on the left-hand side, using the depth information provided, we generate multiple target images. So note that unlike previous other algorithms out there, these target images also contain defocus parts, meaning there is a sharp target image, but there is also the defocus part at each target, like a focal stack. The other algorithms out there simply forces an optimizer to paint defocus parts black, which is not natural, right? So you would expect a blurry version of the same image to appear in that location. But we don't do that. As we know, this damages the outcome. So the rest of our pipeline is a loss that pays special attention to sharp parts, and while the defocus parts are cared less through a weighting mechanism. And in the rest of this pipeline, we provide multiplying targets and loss functions to an optimizer of your choice. We tested this on various approaches, various different optimizers basically. including vanilla gradient descent, stochastic gradient descent, and the Gershberg-Saxton method, which is a very common method in the literature. Our code is available at the following link, as you can see. And this work will appear in IEEE VR 2023. You can also grab a copy of this work on archive if you're interested. So I showed you some blocks, and I told you that this is the 3D hologram generation pipeline, but I need to just prove it now, right? So in order to prove it, I need to conduct some experimentation with our pipeline. We built a phase-only holographic display just for this purpose, with a 1080p spatial light modulator, fiber-coupled lasers, lenses, apertures, and optomechanical components. You can see a rendering of our display on the left-hand side and an actual photograph of our benchtop display hardware on the right-hand side. So this is the display hardware that we are going to use to experiment with our pipeline. So let's see if our pipeline works. So the results coming out of this prototype shows promises in terms of image quality. Here I show a sample focal sweep, meaning I'm changing the focus of my camera and taking pictures from different depth levels. From our prototype, you can see the different portions of the display is getting in focus, and different portions of the display, the images, the scene is getting out of focus. So this is for a 1080p display prototype. We later ask ourselves, if we had like a higher resolution modulator, would things improve further? And we eventually build another prototype with a 4K modulator. I show a focal sweep, meaning I'm just sweeping at different depth levels, and this is with the 4K prototype. So the elephant in the room image obviously improves in terms of image quality and details and so on. So the elephant in the room is, can this pipeline that I'm describing right now and the holographic displays, can this be the projector that the beaming displays need? Can this be helpful to improve the resolutions of beaming displays from 7 cycles per degree to something more meaningful? Or can this be the pipeline to help improve the field of view of the beaming displays, which is just 35 degrees? Can I make it larger with the help of holography? Or in other question you can ask, like, can we replace that bulky optics of the eyepiece? You may recall this birdbath optics I'm speaking of. Can we replace all these things? Can we improve beaming displays with more diffractive and holographic components? And the answer is completely yes. And we experimented most recently with a better version of beaming displays, which involves also holographic displays. Here you see our layout for a beaming display, new version of our beaming display, with a brand new holographic projector, and we branded as a HoloBeam, the name of this project. This work offers a dramatic improvement over beaming displays, but lacks the tracking capabilities of beaming displays that I showed you before. It doesn't involve any tracking. So you can see how we replace the bulky eyepiece I showed you before. Remember the birdbath optics, with paper-thin holographic optical elements, or just a lens basically. And we improved the resolution of beaming displays from 7 cycles per degree to 24 cycles per degree, while we improved the field of view from 35 degrees to 70 degrees. So this work will also appear in IEEE VR in 2023. And I will not go into the technical details for now for sake of time, but I encourage you and suggest you to attend our presentation at IEEE VR this year. You can also find a copy of our work in archive if you just type in HoloBeam. So that leads to the third project that I'm going to introduce today. I would like to discuss today a foveated rendering related project, and this foveated rendering, how this foveated rendering methodology could be coupled to computer-generated holography, and simply how perception could improve holography in the near future with the help of gaze tracking. Let's also look into this. So in case you're wondering how metamerized images are compared with ground truth images, I want to show you this specific slide quickly so that you can have a visual comparison. I don't know what kind of a display you're looking at right now, but if you're at the right distance with respect to your display, metamers are the images that could replace an original image without getting noticed. And especially this is important for the peripheral vision, because that means I don't have to be accurate in painting the colors or painting the structure in the peripheral vision, meaning the parts that I'm not looking at. Then I can maybe get away with less pixels, or I can maybe get away with less details in an image as long as it's statistically correct for my eye. So this works. People know this from before. This works in conventional displays, but can it be also helpful in computer-generated holography is an open question. So if you have some sort of gaze tracking and involved, in this case, we don't have a gaze tracking. You're just looking at some display, but you can pretend to look into this red dot in the middle. The hope is that you won't be able to tell if you're looking at a metamer or a complete image in your peripheral vision. So all the grass and all these details would look as if you would perceive if there was no metamerized image. I hope this concept is clear. So in SIGGRAPH in 2021, we published a paper introducing this new foveated rendering pipeline. Solely relies on a process called metamerization, as I described. And we rerun this at interactive rates. And foveated rendering is a method that renders content more detailedly in the locations you're gazing at in a given scene. This way, images look perceptually accurate, but not full resolution. And having no full resolution in near-eye displays is very helpful, because now you can get away with all these hardware constraints. You can relax the constraints, and you can build the display we all want that is going to look perceptually realistic to you. It's much needed in the next generation displays to make them less demanding, especially in wearable displays for augmented reality and virtual reality. Second benefit is the metamerization is an explainable perceptual process in your visual system. So we can turn this into some sort of loss function. We can make a differentiable version of it. So we actually did that as well. And this differentiable version could help us to formulate some loss function. And we can use this in our optimizations in holography, for example. So let's also understand this. Now that we have a means to optimize our holograms from before, as you may recall, this is the same, more or less the same pipeline I was showing before, but with a different loss function now, where mathematic loss function is also involved. We can make a gaze contingent version of the holographic display that we were discussing before. Here you see again a hardware to test our gaze contingent perceptually guided holography pipeline, and you see the images coming out of our pipeline. This is a simulation results, but you can also find experimental results in our paper. Here you see at the point where you should be gazing at, this is the red dot. If you gaze at this red dot, if you're at the right distance with respect to this visual, you would be seeing the parts that you're not directly looking at as completely normal, completely looking okayish for you, let's say. So you can fool the eye. So this relaxes the optimization problem, because now we don't have to be very precise at every location in a holographic display. And we know that holographic displays, they often have these noise patterns called speckle, right? Maybe we can distribute the noise patterns such that they are not perceptually visible in the peripheral vision. So that was the interesting bit for combining perception, foveated rendering, and holographic displays. So it makes sense now to survey the next. What could be important in the future? What kind of aspects of holographic displays or displays in general could be meaningful for people that are newcomer to this field, or maybe experts in this field? I'll just make a wish list here and just talk about a few papers that I observed from literature. I find this idea of learned eyepiece approaches for increasing attendu, meaning the eye box. The eye box is the location where you look into the display and you're able to see an image from that display. That eye box is very limited in holographic displays, and people recently started with playing with this idea of optimizing these eyepieces such that they allow for wider eye boxes, and there are learned approaches for these, like where they combine deep learning methodologies with these, or optimization pipelines with these kind of approaches. So I find this pretty important, and I left here 3 different papers that you might be interested in looking into if you're interested in this field. And regarding the perception, I think computational models of color or a virtual observer could be highly beneficial to displays to unlock new potentials, in my opinion. And also perception and eyesight with these new emerging displays should be revisited, because holographic displays, they work differently. They work different with respect to conventional displays. So we need to find new recipes to compensate for prescription errors or your eyesight and so on, so that we deliver the right experience for you. We can tune the display for you, and holographic displays have more programmable, capabilities, let's say, that helps us do that. There may also be more straightforward means to model displays in simulation. These light transport related papers that appeared in the last few years are also interesting, because it can help us to fix the imperfections in the displays, especially in the hardware. We can learn the hardware by looking at some samples, and then we can say, I need to place this type of a hologram so that the image look more correct, free from all these artifacts that we were seeing before. That could also be learned, and that could also be relying on a learned model, on a deep learning model. So for off-axis geometries, for example, if you have tilted displays, or like if you have a surface that there's a slight tilt, unintended slight tilt, maybe you can get away from all these imperfections with learning approaches. This may also unlock new capabilities in the future. So another thing that is interesting to me is in hardware, in my opinion. So it's the room scale wave fields. Some people are trying to build holographic displays that are room scale. So you don't need to just wear it. You can just look at it, stare at it as if you're looking at a desktop display. And that is also an interesting development. And there's one paper that I'm aware of that is very interesting. If you're curious, you can also take a look at it. So, but beyond these, personal opinions, let's say, I also looked into the results of the other generative models, and I question many things, including display hardware research. But it's a very powerful tool if you think about it. Typing keywords and generating perfect images, videos, and even 3-dimensional objects is definitely out of this world. But I bet I'm not the only person thinking like this, and many people started to be more, vocal about it. And there's an emerging work that you can search and find out today, and for augmented reality applications, virtual reality applications, people try to merge these diffusion models, for example, with these kind of approaches, these kind of displays, variable displays. I bet there will be many other ways that generative models could help our display research. And that's something we should also think a little bit more about. So beyond this surveying the next, let me move on to serving our community section of my talk. Please allow me to highlight a few efforts from our side towards maintaining a healthy research community. We moderate a Slack group with more than 280 members. The topic of the discussion is around rendering, cameras, displays, and perception. The group is public, and interested parties can join by following the link. And we recently delivered a lecture in SIGGRAPH for optimizing vision and visuals, and we have a great set of collaborators here. Our hope in doing so is to provide a guidance to newcomers in the field. If you want to start in this type of research, I think you can just go through this lecture and learn a lot from the actual experts in the field. So more details of the recording of our lectures and materials used in these lectures are available also in this link. So we also organize weekly seminar series like the one that I'm just giving right now These events are an excellent base for our students and academics to draw inspiration. More details, such as our mailing list, are available at the following link. And I'm proud to say I'm actively helping and supporting Optica's display technology and group, and play the essential roles in organizing recent events, like including AR/VR Team at Optica's Frontiers in Optics. Last but not least, we also maintain and develop an open source library for optical sciences and visual perception. All our recipes derived from our research, they are all included in this library. They are all differentiable, by the way, which you can optimize using your learning methodologies and so on. For example, I talked about mathematical loss, right? And mathematical loss is a function, is a differentiable function in this library. Or I talk about like how to optimize a hologram, and this is also another function you can find in this inside this library. Here comes my favorite slide in every presentation, the conclusion. So after a brief introduction, I argued that displays are an essential part of our lives. We all see the future in AR and VR. And I proposed beaming displays, which suggests removing many parts, many components in an near-eye display and make it all passive. I also introduced a multiplanar holography pipeline for high-quality image generation and argued that this could help beaming displays in the long run. I've also shown workflows where modeling perception, simplifying hologram calculation. So I have briefly discussed important works from the others in the field, and I gave examples of how we engage with our community in public and help maintain a healthy community. All of this work is made possible by collaborating with an excellent set of collaborators. These people are listed here, and I'm forever thankful and grateful for their support. With that, I conclude my talk, and I'm happy to answer your questions. Thank you for paying attention and listening.
Thank you, Kaan, very much. Thank you.
Thank you.
Yes, the floor is open for questions. You're welcome to raise your hand. You're welcome to type it in the chat. If you are in German,
let me start by asking a question then.
Oh, go ahead.
First. So Kaan, it's a very nice talk. Enjoyed it very much. I know you are using lasers for making these holographic displays. So you must be planning to use 3 colors, red, blue, and green, I guess, to make a real image. I mean, is that the plan, to have a 3 separate lasers used in those displays, or what is your plan to make a realistic image? I mean, I guess.
Yeah, that's a great question, and that's also an important question for us. I will first explain the traditional way. The traditional way is to use one programmable diffraction grating, spatial light modulator, and then using 3 different lasers, and they just operate one by one: red, green, blue, red, green, blue. But there might be in the future new ways to formulate this problem. Let me say that this is the existing way. There are other things I cannot talk about right now, but yeah. So the traditional way is people use RGB time sequentially,
Right.
but this is not enough for sure. I think this has to be different. Let's say. Yeah.
I see. Very interesting. I see. Okay. And the other thing I wanted to mention was that in the last maybe 10 years, in optics, people are now moving to a direction called meta surface. Meta surfaces are like diffracting optical elements, but they are done in a different way. Sometimes they are metallic objects, but this is getting very popular, meta surface, and I'm sure this could be used for your displays as well. I mean, so this is just a comment. I mean, not a question, I guess. Such.
Mm-hmm. No, I fully agree with this comment, and I think there can be ways to just combine these 2 things maybe in the future. Yeah, so there are opportunities over there. I think meta surfaces are very important, I think, in this research. Yeah.
I think Jim has a question. If I see his hands.
Yeah, Jim, go ahead.
Yes, thank you. In your earlier talk, you mentioned that the projected display was limited to what I believe was about 7 cycles per degree. What was the attribute that limits the resolution to that value?
That's a great question. Thank you very much, Jim, for asking this question. There's this concept called Rayleigh resolution. So when you have a certain optics, you design it with a certain aperture and a focal length, and this limits the footprint of your one single pixel on a spatial light modulator on the final image plane. So in other terms, the smallest pixel you can support is limited by the size of your optics and the focal length of your optics. And that is the problematic part in this implementation. In this implementation, as you can see, we use a very limited aperture size. These are just 1-inch lenses, as you can see.
So that's the 1 inch actually at the projector then.
There are two things happening here. One of them is about the lenses. They can be in larger aperture size to support to support higher resolutions. But there are also things we cannot manipulate in this setup. This projector is designed with certain characteristics, right? So this projector, the way a single pixel is being emitted, or let's say the extent of the rays are designed with certain angles, right? Like it cannot be, like we need to first widen that, maybe using additional lenses in front of it, and then let it go through this larger aperture structure. That there might be a solution like this to improve the resolution of this display if you don't want to use holography.
So what I'm hearing is basically the spatial frequency footprint of your projector is incapable of presenting an image to your wearer's, I guess you call it birdbath optics. So the limitation then actually comes, am I correct that the limitation comes from the projector system?
The limitation is coming from the projector system, because you can also, verify this very easily. This is an off-the-shelf birdbath optics, meaning we harvest that thing from an existing near-eye display, existing augmented reality display. And that display supports high resolutions with respect to what we are displaying here.
Okay.
So,
Okay.
Yeah.
Thank you. That answers my question.
Okay, thanks.
Jim Field.
Oh, hi. Could you look at the slide that had the peripheral vision blurred for a second? I want to ask you a question about that, like slide 28 or 30. Yeah. Now, it turns out that the peripheral vision stuff, as you see in the lower left, actually has a lot of really fine detail in it. It's just not the fine detail of the actual original picture. So it seems to me, in terms of number of pixels to represent that, it would be comparable to that if you just showed the regular full resolution image. Can you comment on that? Does that really save you anything in terms of display number of pixels required?
For the time being, it doesn't save much. So for the time being, there's no saving. Like if you just use it with a conventional display, you still have to paint all these details, right? But displays, as we know them, just we're painting pixel by pixel. This is only one way of painting an image on a screen.
Yeah. What if you just showed a blurred version of it with fewer resolvable elements? Would that give not as good of an effect?
So we have also a subjective experiment on this, and the users we had the subjective experiments with, they like this version better with respect to the blurry version. So not sure if this is an answer to your question. You may get away with blur to some extent, and there are also works in the literature which you can find, just foveating by using blur and enhancing the contrast of the blur. But these works, I'm not sure if they are as effective as metameric versions of it. So I don't think they are the true solution. Let's say it's a solution, but is it the solution that can replace the ground truth image? That I'm not sure.
Okay, thanks.
You're welcome.
Any other questions?
Anybody from the room there?
Yeah. Anybody
And
from the room?
can you hear me?
Yes, we can hear you. Go ahead.
Okay. This has to do with the use of diffractive optical elements. Of course, the use of diffractive optical elements in visual systems goes back a long way. There was a lot of work back in the mid to late 90s. And what made a lot of that effort so difficult and ultimately hurt the commercial success was not the design. They were able to design high quality elements, and it wasn't the fabrication. They were able to fabricate elements. It was the residual scatter. And so the question is, what is being done in the community to do high dynamic range scatterometry measurements on some of the diffractive elements? Because sometimes, even a 0.1% scatter can produce too much haze in a visual system.
Yeah. If I understand your question correctly, you're talking about artifacts such as, for example, speckle is one thing you're I think highlighting, and the other thing is
any source of scatter, any tendency for the light to go in a direction that it's not designed for. Of course, if it's coherent scatter, then it causes speckle, and it's a very distracting thing. But even if it's incoherent scatter, it can still cause a background haze in visual systems and a reduced contrast. So I was just curious to know what the gold standard is out there now in the AR, VR world, what measurements people are doing in order to characterize these components.
Okay, so if you're talking about, of course, there are many different diffractive components we can discuss about, but let me limit my conversation to spatial light modulators. If you're talking about spatial light modulators, they are nowhere near perfect. So there are non-linearities in these devices. I'm speaking about the liquid crystal versions. So if you want to tune into a certain phase, you don't necessarily get that phase every time. It changes with heat and so on. There are all these imperfections and non-linearities in such systems. So speckle is always a problem, or any other scatter that unintended scatter could always be a problem in these displays. And there is an active research on this, like people try to suppress speckle by using coherent light source, coherent but partially coherent light sources like superluminescent diodes, for example. That's one thing that they use to overcome such speckly patterns, for example, or they use temporal multiplexing in their displays to smoothen the effect, basically. But as you mentioned, the dynamic range becomes a trade-off, meaning if you want to have true dark levels or true highest brightness possible, this is always limited by these imperfections in this system. And I don't think it's going to go away easily in the next 10 years. There will always be, non-linearities in spatial light modulators, although there are these new emerging light modulators that are temporally multiplexing, like the ones from Texas Instrument, for example. They use piston mode phase only DMDs, for example. They build these kind of devices. But these devices, they are also very limited in terms of phase resolution. Like they only have 4-bit control over the phase, whereas the liquid crystal ones can be like 8-bit, for example. So that means that's also limiting the dynamic range you can expect from a display, because it's also temporal multiplexing. You can interfere in one frame, but you cannot interfere between frames. Therefore, you're adding light on top of light in your perception, and you're getting this image reconstructed on your retina, which is in terms of dynamic range is a limiting factor if you think about it. So all these things, all these imperfections will always be in place. So then it boils down to the case of can I get away from some of these things by using perception? For example, this metamerization I was talking about, maybe we can in the peripheral, because let me show you this slide one more time. So if you look into this slide, this is the result we were getting from this mathematic holography pipeline. Maybe you can redistribute the speckle noise in the peripheral vision such that it's acceptable for any human observer. But for the fovea part, for the sharp parts, maybe we do something different in the future to get away from all these, dynamic range related issues or like sharpness related issues. I'm not sure if this is an answer to your question because it's a very broad question. I tried to, survey different parts of the problem.
Yeah, no, that's helpful. I was more curious about how the devices themselves are characterized and what measurements are being made on the devices to quantify the scatter, apart from just things like image contrast.
Wait, just to see if I understand you correctly. When you say scatter, you're talking about the scatter on the modulator, or are you talking about scatter on some other optics in the system?
So if you eliminate, for example, a spatial light modulator, and that spatial light modulator is configured as a grating,
okay,
then light will scatter into certain diffracted orders that it's designed for. But there's also a lot of other light that is spread around. And that happens from edges, that happens from irregularities. And of course, it depends on the nature of the particular device and the particular type of diffraction grating. So it happens with all of diffractive optics. And so the key is you have to somehow quantify that, and you come in, and usually what's done is you measure light over, full 2 pi steroradians to find out where the light is going, and then you characterize it that way. But that's sort of general optics. I wasn't sure if that sort of thing was being done yet in the AR/VR community.
To be fairly honest with you, I don't know the answer to your question, but I can elaborate a little bit more. I think like when you say like scattering, you're referring to, for example, there's a diffraction efficiency of the system, right? Like the amount of the light that is diffracting from this system, the ones that we want to, steer in a certain direction, let's say, or do certain things through diffraction. And there are these, there are these, there are these components that are just directly bouncing zeroth orders, and that some of these zeroth orders is unmodulated light because of the diffraction efficiency of the system. One way to get away from these things is to shrink the size of a pixel, have a smaller pixel size, so that most of the light diffracts in the way intended. On the other hand, maybe another source of scattering, related to your question again, maybe another source of scattering. Let's look into this diffraction grating. It's a simplified diffraction grating with a bunch of blocks, right? And if you want to build such a device, there will of course be light beams that will be just bouncing off this device, diffracting or bouncing, and maybe ending up at a different location on the diffraction grating because of the height differences. And maybe it's bouncing again, and then things starts to get a little bit weird in that case, right? So all these things are very much dependent on the structure itself. For liquid crystals, it's a different story, I guess. And also for diffraction gratings like this one, it must be a different story. But I don't know if there's a gold standard for these things, or I don't know if there's a way to quantify these things in a classic holographic displays for augmented reality or virtual reality.
My understanding is this unwanted diffracted light will become the stray light in the imaging system, which will reduce the signal to noise ratio. So this unwanted stray light will get onto your imaging. So how do you handle, this, because this stray light will reduce your signal to noise ratio. Then do you have a way to, compensate it and still keep the certain signal to noise ratio on your imaging? I think that's the point.
Okay, so one way I can propose, let's say, is we have a paper back in 2022 related to light transport, and we learned the light transport kernel for our own system, for our own hardware, with all the imperfections in the place. We put a hologram into our holographic display. we capture an image coming out of our holographic display, and we try to find a correlation, a model that models the entire process of hologram to the image with the hardware included. If the scattering, or if all these problems that we are talking about are due to imperfections of the system, there might be a way to learn them, and there might be a way to build models, statistical models, that may be able to compensate for these things. This is just like we have some preliminary work on this, where we show improvements over the over the traditional method, but to truly fix all these issues we're talking about right now, I'm not sure if there's any model out there that can help you with. But this is an active research topic again, to learn the imperfections in a holographic display, such that you can account for all these image distortions that are unintended, let's say. Not sure if this answered your question, but
there's a question on chat.
Yep.
Chat also from Jason Tiner. Jason, you want to ask that question, or do you want us to read?
Let's go ahead, read it. Go and you can read. Okay, do you want to read?
Yeah, you can go ahead. Yeah.
Okay, so the question is, are you familiar with image reconstruction from multiple apertures or planoptic imaging, where depth information is readily manipulated? Seems like there were parallels when you were cycling through different depth focal planes. Are there any similarities in how the technologies are tracing ray paths?
There are definitely similarities between planoptic imaging and holographic displays. The holographic images that I was showing, they have a single perspective. You can think of it more like you're always looking from a single direction to that display. But in reality, what we want to achieve is a display that you can look from any other perspective, any other direction. And that's where these multiple apertures come into play. That means we need to create different viewing places, viewing windows or eye boxes, so that will capture a different perspective of the scene, that will show the different perspective of the scene that we are trying to show in a holographic display. So assuming you can capture such things, for example, through multiple apertures in planoptic imaging, then the question is like, how do you formulate that as a hologram? That's also an active research field. There are some works which I can refer to, of course, for example, Chakravartul et al., SIGGRAPH 2022, which deals with modeling all these, different perspectives in a holographic display, so that it can be viewed from different perspectives, different places in front of the screen. But this is a very active research field. One thing I want to highlight about holographic displays is it's really, really emerging. Like if you compare it with, for example, ray tracing, or if you compare it with planoptic imaging, these are readily matured technologies. But holographic displays, in the last 2-3 years, there has been a revolution in this space. If you look into the literature back in 2018, 2017 timeframe even, you would see a large difference between image quality. So that's also something to bear in mind. So it's many things that we're discussing here are active research topics, open questions.
Thank you, Kaan. And Govind, I think we are out of time, right? So I don't know if there are any further questions, but
I don't think so. I think we can go
okay.
ahead and close
Okay.
the talk at this point.
Okay, great. Well, thank you so much, Kaan. This was an amazing talk, and thanks everyone for attending. And goodbye. Thank you. Bye. And the recording, I think the recording of the talk will be available for people who want to view it later.
Yeah,
Thanks,
and I also want to thank Kaan for giving this talk. We enjoyed it very much. Thank you for your time and effort.
Thank you, Govind. Thank you, Mijlat. Thank you for having me.
Goodbye, Kaan.
Have a
Bye.
wonderful day. Bye.
Okay, bye.
Thanks.